Today in section 9.2, we are going to see an incredibly important definition that goes hand in hand with vertical asymptotes. And between the two, you have to fully understand them if you ever want to understand what a limit is, if you ever have to study calculus. So here's how we begin. We are very, very familiar with a non-permissible value. We've seen this before. If you had an equation like y equals 1 over x minus 5, x could never be 5 because then you're trying to divide by 0. The first time we saw that, we just called it a no-no, you can't divide by 0, and we saw it in a few scenarios. And then we labeled it. We called it a non-permissible value, and here's what we then discovered. If you had an equation that looked like this, a function, and you graphed it, at 5, there was a vertical asymptote. The graph does not exist there. It never crosses the vertical asymptote. It only approaches it. It never touches it. And so then you thought it was a done deal. But there's something else. And this is brand new. You would never have seen this before. But again, it's critical to understand the difference between these two. And then you can move into a study of limits. That's the first of the big 3 concepts in calculus. So the name of it is called the point of discontinuity. And if you had a graph that showed this type of idea, there would be a little hole, hence the nickname. That's what it's basically called. Okay, so there's going to be 2 different things. Now, what we need to learn today is, how do you tell? How do you tell when it's going to be a vertical asymptote or a point of discontinuity given a graph, and they're both when you're trying to divide by 0. So here's our first example. We are given the function f of x equals x squared minus 6x plus 8 over x minus 2. So then if we said, just what is the non-permissible value, the no-no, x could never equal 2. So that's very straightforward. But then here's where we have to move to the next level. The question becomes, if we graph this at 2, is it going to be a vertical asymptote? Or is it going to be this strange new thing that you wonder how it can possibly come up? Is it going to be this point of discontinuity? So here's how we begin. And this one is going to be no surprise. You'll look at the numerator, it is jumping off the page and it's like slapping you saying, please factor me. And so we will. We will factor the numerator into x minus 2, x minus 4. And then if we just go back in time, one of my favorite things ever to do is to cross this out. And here is what we are left with. We are left with y, or f of x, is equal to x minus 4. Now, I'm going to have to erase just to kind of show the idea. And I'm going to erase up top just so we can still use the equation right in front of us. Here is the idea. When we take a look at what would the graph look like of f of x equals x squared minus 6x plus 8 over x minus 2. It is not as crazy as you think. Many people would be like, this has got to be the craziest, wickedest graph ever known to man, but it's not. Actually, what this graph looks like is almost identical to f of x equals x minus 4. And so f of x equals x minus 4 or y equals x minus 4, that's just a line. That's just a straight line with a positive slope. It has a y-intercept of negative 4. The slope is a 1, so it goes up 1 over 1. If I was going to draw that line, it would just look something like this. But stop. Here's where we are. Here's where the difference comes in. In this graph, and I'm not going to get it perfect because my artistic abilities aren't that amazing. If we go to 2, okay, so if we go right to 2, there is going to be a little bit of a problem. At 2, there is going to be a hole. Now, you guys, I was just drawing it just to show the idea behind it. Please forgive me. I don't know exactly where the hole is going to be, but you could easily calculate where the hole is. In the notes, I had it up here, but here's the idea. What we simply do is we go out to 2, and we find, okay, that instead of it being just a straight line like this, there's actually a hole. Now, how do we know that? Well, it's because of the cross out. That is the key. So this graph is not really crazy. It looks almost identical to this graph, except there is going to be a hole at 2, not an asymptote. So the rule is anytime it crosses out, it was actually a hole. And you could confirm it. You could use one of the big graphic calculators at TI, or just grab your phone, your computer, and go to a grapher. There's a lot of those available, and graph this original equation, and you'd expect to see something crazy and wicked, but you'd see basically a line, and if the grapher is strong, it could show a hole. So let's see that again. In the second example, we won't really change much. We'll just say consider y or f of x equals x squared minus 1 over x plus 1. Now here's how we begin. Number one, we first of all say, what is the non-permissible value? Well, you look at the denominator. X could never ever equal -1. Then you're trying to divide by 0. It's our classic no-no. But then here's where we have to change. It may or may not be a vertical asymptote, and you have to investigate. So what we will do is we will start by factoring. The numerator factors to x minus 1 and x plus 1. The denominator, x plus 1, and here's what happens. They cross out. As soon as the problem crosses out the no-no, it automatically rules out that it's a vertical asymptote. It becomes a point of discontinuity. The nickname is a hole. And then here's the idea. This original graph is not as crazy as you think. It is going to almost exactly resemble just the very, very simple graph y is equal to x minus 1. And so what would the graph of y equals x minus 1 look like? Well, it's just a straight line that has an intercept of -1, a y-intercept, and then a slope of 1, so up 1 over 1. So I'm going to draw this line. It's always kind of good to be working in something that's erasable. Here is the only difference. The only difference between this original graph that, again, you think is quite crazy, and then this graph over here is that instead of there being a vertical asymptote at -1, there is a hole. So we go to -1, we go and we find the graph, and there is going to be a hole. And again, many graphers can show that. My calculator, which isn't that bad but not that new, sometimes just shows it like a line. It struggles to even graph the hole, but that's the difference between this equation and this one. And that's how we know that there's going to be a hole there. And if you wanted to find the height of the hole, we'll just simply sub in. Put in -1 right here. -1 minus 1 is -2. That would be the height of the hole. And anyone who knows calculus already would know that's a very important idea in limits. And so you could go back to number 2, our first example, and do the hole a little bit better. I don't think we placed it properly. Now, for our final example, what we're going to do is show just one more option, and then we won't go beyond that. This will be kind of the level to understand the hole. So we just wrote down the word consider again, and we have the equation y equals x minus 3 over top of x squared minus 9. So this guy. You look at it, and first of all, if we were going to say, what are the non-permissible values? What could x never ever equal? Well, there's actually 2. It could not be -3, and x could not be +3. Just imagine putting both in, you'd still be dividing by 0. So then here's where the thing comes in. There's 2 points right here that are non-permissible values that are no-nos. Maybe they're asymptotes, maybe they're holes. You have to investigate. And the investigate is very obvious. What we are going to do is factor. And I just want you guys to make a note that in the previous 2 examples, the factoring we did was up top. Now we are factoring down low in the denominator. And here's what happens. These 2 cross out. So what would you be left with? Just a 1 over top of x plus 3. Anything divided by itself is 1. The 1 keeps your place. It reminds us the x plus 3 is in the denominator. But then here's the culmination. We actually had 2 non-permissible values. We had a non-permissible value at -3 and at +3. You can see that right away. You can even see it here, swoopy swoop. You can even see one of them right here, that x can equal -3. Now here's the idea. The x equals -3. Just imagine again a -3 right here. This is a vertical asymptote. So at -3, I can right away put down a vertical asymptote. But here's the difference. At +3, that is this one right here that got crossed out, that is going to be a hole, the nickname for a point of discontinuity. Then we would have to say, well, okay, what would this original graph look like? Well, it's going to be incredibly close to this graph right here. And I'll just do it in red so it stands out. This graph right here is an oldie but a goodie. This goes back to pre-calc 20. It was the first of the kitty corner days. The horizontal asymptote is just at a height of 0. And if we were going to figure out, okay, what does this guy look like? We would find the y-intercept, sub 0 in for x. The y-intercept is 1/3. We would know then that it must come from this asymptote and approach the horizontal. And then it jumps kitty corner, working backwards. Now, just if you watch carefully for a finish, this is the idea. This original graph looks almost identical to this graph. They are so close to each other because of the crossout. There's only one difference. The only difference is in the original graph, if you go out to 3, there is actually a hole. That is the difference. And it's a very, very important thing. If something is in the denominator and it does not get crossed out as a vertical asymptote, if it got crossed out, the non-permissible value, the no-no, then it was a hole. And there again is something very important. I'll give you a little flash of calculus. If you approach this asymptote, you never ever stop. You just keep going down to negative infinity or backwards up to positive infinity. It never stops. But this hole has a height. It has a height. That is where a limit goes, and that's why this is so important to understand the difference between these two concepts.